today we're going to start 13.4, which is motion in space. We're going to talk about velocity and acceleration. So we're going to show how the idea of tangent and normal vector and curvature can be used in physics and study the motion of an object, including velocity and acceleration along a space curve. Okay. So suppose a particle moves through space. So imagine this is a particle moving through the space, okay? And the position vector at time t, so this is the position vector at time t, rt, okay? And for a small change in time, h, okay? Think about h is a small change in time, okay? Then after a small change in time h, then the particle is moved to here. And then we have the new position vector, r of t plus h. Now, if we think about this difference quotient, okay, r of t plus h, subtract r of t, and then divide by h, we got a vector pointing this way, okay? And this is a 1 in the blue rectangle here. This vector here approximates the direction of the particle moving along the curve. Okay, so think about it like kind of the secant, right? A secant trying to approximate the tangent, right? This one here approximates this, okay? Its magnitude measures the size of the displacement vector per unit time, okay? So this is the displacement, subtracting the two positions here, you get the displacement, and then the t here, h here is a change in time, okay? So this is it measures the size of the displacement vector per unit time, okay? This vector over here, I'm gonna label this 1, okay? That gives the average velocity over a time interval of length h, right? Kind of familiar with the two-dimensional case, right? So how do we figure out the average velocity? We use the final position, subtract the initial position, and then divide by the h, right? Divide by the change in time, the time elapsed, right? So that's now the average velocity. And we take the limit of this average velocity as h approaching the zero, and make this time interval to be smaller and smaller and approaching the zero. And that is equal to the instantaneous velocity at that time. Okay, this is not the two-dimensional case. And as you can see here, if you look at the graph, this one here, as the h here approaching the zero, then this is going to approach to r prime of t. This tangent vector over here, right there, okay, this approaching to this. So the velocity at time t is actually the duality of r at time t. These two are the same thing. So I use the same color here. You can make the connection there. So the velocity at this time t is the duality of r at time t. Okay? This is the velocity. Okay? So the velocity vector is also the tangent vector and points in the direction of the tangent line. Okay. As you can see here, it points in the direction of the tangent line right there. Okay. Now the speed of the particle at time t is the magnitude of the velocity vector. How do we find speed? Speed is the magnitude of the velocity. So for magnitude, we put the absolute value there, right? And we can just figure out what's the magnitude of the velocity, and that will be the speed, okay? Speed is a scalar, okay? It's a magnitude, okay? Velocity is a vector. It has magnitude and also direction. Question? Okay. So now we can make the connection between the 3D and the 2D, okay? We can see that was appropriate. The velocity vector, okay, is equal to the vector r prime, okay? And that's equal to dsdt. This is a change of the r with respect to time, okay? That's rate of change of distance with respect to time. Rate of change of distance with respect to time, okay? So as in the case of one-dimensional motion, right? Remember when we have 110A before, what do? We do that. Acceleration is the derivative of velocity, right? And it is the second derivative of the position function, right? So this is r double prime t. Okay, very similar, right? Okay, now let's look at some example and try to understand this a little bit better. Okay, and let's do this together. Okay. So the position of I'm gonna ask someone to read that. How about Raymond? Could you read this from here to here?
The position vector of the object moving in the class is given by r of t equal to t cubed I plus t squared j. Finding its velocity, speed, and acceleration when t equal to 1 and illustrate geometry.
Okay, thank you, Raymond. So now, in order to find the velocity over here, right, we are given this is it's like a position function, right? The vector is a vector function of this the particle. Okay, so to try to find the velocity, we're given this. What do we do to find the velocity?
Take the derivative of r.
Take the derivative of this, right? So if you take the derivative of this, what do you get here?
3t squared plus 2tj.
Yes, you got it. Good. So, and how do we find the acceleration?
Take the second derivative of rt.
Right. And then we differentiate it one more time, then we get the acceleration, right? Okay, good. All right, you got it. Okay, so you just differentiate first. One time you get the velocity, differentiate one more time, you get the acceleration, right? Okay. And how do we figure out the speed? It's a magnitude, right? So we just figure out the magnitude of this. We'll take this square root of this square, 3t squared, and then plus the square of 2t. Okay, so this is the speed, okay? It is a scalar function, okay? So when t equal to 1, we try to figure out the velocity at time t equal to 1, right? So what's v1? How do we figure this out? Substitute 1 into the velocity function, right? Okay, how do you figure out a1? Putting 1 into the acceleration function, right? And then for this one here, the speed, you just substitute 1 into the speed function, right? Okay, good. Now we're going to graph it, okay? So we're going to illustrate this, graph it, okay? So actually, I graph it over here. In 3D, it looks like this, okay? This is, it only has the x and y. It's on the xy plane. Only have the I and j component, right? So it's on the xy plane, okay? And then this is a graph, okay? It's totally on the xy plane, okay? Then what happens when t equal to 1? T equal to 1 is at this point 1, 1, like that, okay? So if you're looking at the xy plane, so 1, 1 is right there. And the velocity vector at 1 will be this one over here. How do you draw it? You will go at 1, 1. You go 3 units, 1, 2, 3, and then you go up to 1, 2, and then you draw the vector there. And for the acceleration vector at 1, you can. This is 6 and this is 2, so you go 6 in the x direction and you go up 2 in the y direction and you draw the vector. So you get the 2 vector there. Okay? Question? All right, now I'm going to let you practice on this. How about you guys practice on this or working maybe a group if you want, okay? So try to figure this out.